So let's look at a problem that involves solving a trig equation with fairly realistic complications, but not too many unnecessary ones. Like I do a lot of my classes, we're looking at wind turbines, and we're looking at a situation where the height of the tip of a wind turbine blade is modeled by this sine function, t is in seconds, h is in meters, and I want to know, find all times in a specific interval in time, let's say 2 seconds before I start the stopwatch and 2 seconds after, at which the tip is a specific height, namely 5 meters below its maximum height. So how you solve this problem depends a bit on how much technology you have, but let's suppose for a second that you actually had a calculator available um, that lets you graph, and um, then what we could do is we could look at, well, what is that maximum height? That's pretty easy to find. You're definitely going to need that for any way you solve the problem. It's going to be the centerline height plus the amplitude is 105. We're interested in 5 meters below that, so 100. So what I've gone ahead and done is graphed, excuse me, this function. Notice that this is not going down to 0 on the axis here. It's only about like 55. So the 0 would be way down below. But it's graphing the height as this sinusoidal function, and as advertised it goes up to 105, down to 55, and we've also graphed the 100, and I've graphed it on the interval from t from -2 to 2, and we see that there's 6 times when this should happen. Okay, and as is usual, there's going to be 2, very common thing is 2 for each cycle, and so that should be showing up. Okay, so another picture we could have is, I'm going to give you a sketchpad picture here. Okay, so here's the ground, the bottom of the pylon of the wind turbine, and then up here at 80 is the center, goes up to 105, down to 55, and it's whirling around like this, and we're interested in boom, boom, and then again, boom, boom, and then again until I'm outside of my interval. Okay, and notice that this one, because it's a sine function, it starts at its midline. That's an artifact of exactly the model that we're using here, but that's fairly reasonable. Okay, so now let's look at how the algebra would work. So we're going to set this equal to 100. So let me take that down here. We're going to strip off that, subtract across the 80 and divide by the 25. So we're going to get sine of 4.60t equals 20 over 25, or 4/5. Or if you like decimals, 0.80. Okay, and here's where we have to figure out, have to use some sort of inverse function. Now, if we were really lucky, this would be like 1/2 root 3 over 2, fairly contrived kind of situation, not likely to happen in an applications problem. So we really will need the inverse sign. Okay, one thing, also, let me put in one thing I often suggest is to separate out the idea of the angle from the time. We've really got our classic problem, sine theta, mystery angle is known value. And then I'm going to put back in the t to deal with that in a minute. Okay, so yes, one of the answers here is going to be an inverse sine, but it's very, very dangerous here because it's really important that that's not going to be the only answer. Now we're going to go ahead and let the computer actually get that. Okay, so that's going to be 0.9273. This is where you want to be really careful that you're actually in radians. If it's a circular motion problem, the default really should be, you should assume it's in radians. Okay, I'll put that in there explicitly though. Okay, and then what's the other angle on the circle that we get? Okay, so let's go back to that geometric picture. That, the claim is that that's about 0.927 radians. It's plausible. Okay, and then what's the other one? Notice that when you're looking at a sine theta equals a constant value problem, it's exactly this picture that you're looking at two angles with the same height. They're reflected across the y-axis, and that's one of the transformations we know. We've studied that. That is pi minus. So pi minus 0.9273. Let's get the decimal for that. And that's going to be 2.2143. Okay, so that's the angle that it's at. So that's sort of physically, if you're looking at the wind turbine going around, what are you going to see the angle is? But we really care about the time. How long does it take to get there? So, but that's not hard because we just plug in substitute back in terms of our temporary variable theta. So that's going to be 0.9273. That's one of them. And so that's going to be 0.9273 over 4.60. And that, I wish it would put it in the right place, but it doesn't. Otherwise, I love this program. So 0.202, we'll probably strip off that last decimal place because it doesn't look like we have those 3 decimal places of precision legitimately. But let's just keep it for now. Or t equals something. You know, I'm going to make a new display because it's just getting too long. That's what's happening here. Or t equals, so let's see, let me actually cut this out of that. So t equals 0.202. Sorry, I know it's bouncing up and down. So let me just write that down. Okay. Or t equals, now I'm going to take that, where was it? The 2.2143. That was the other angle. Divide that by 4.60. Get the number there. I'm going to put that back where I want it to be. Okay, and now these are in seconds, notice. Okay, so let's see if this makes sense. This is something we could have done at the start. I probably should have done. Is figure out the period of this function. Okay, because it's really important, and this is going to be the technique where we're going to get the other solutions, to think physically about, okay, how long does it take to get around once? Well, that gives us an idea of what a reasonable answer is for, okay, getting up here, which is maybe about 1/6 of the way around, here, which is maybe about 1/3 of the way around, and then it's going to give us an easy way to get the other solutions. Okay, so the period here really would suggest actually doing this right at the start. Period's always 2 pi over omega, or 2 pi over b, whatever you want to call it. This thing in front of the t is going to be omega, and we've often called it b as a kind of a more neutral letter. Okay, so let's get that as a decimal. Okay, so really good context here is that it takes about 1 1/3 seconds to go all the way around, and indeed it's taking about 1/5 of a second to get to the first location, where it hits that height, and then about 1/2 a second. These are reasonable numbers because they're small but not tiny portions of one period. Okay, so we've got 2 of our solutions, 0.2 seconds and 0.48 seconds, and we want to know the other ones. So there's 2 strategies. One is to go back to the theta, this angle, and add 2 pi's repeatedly to think about coterminal angles. And then the only thing is that's not the variable we wanted, and we'd have to repeatedly divide by 4.60. It's not horrible, but there's a smarter way to do it, which is these two hits of the right height are going to repeat every period. That's what the period means. It's how often things repeat. Okay, so we're going to get t equals, let's look at the one seed value, 0.202. Well, that's going to work, certainly, plus 1.366, and then plus another 2 times 1.366. But we only wanted to go up to t equals 2, so that's really not going to be necessary. So that is going to go away, but we might have to go backwards in time. I want to make sure that people realize that that's very often legitimate. 1 period ago, that totally works. That's not going to be less than -2. But let's see, 0.202 minus 2 times 1.366? Nah, pretty easy to calculate that out, and that's less than -2, so we don't need that guy. Okay, so not surprising, one of the seed values gave us 3 actual values. Okay, let's go back up to the graph for a minute here. There's the 0.202. Okay, that makes sense. Then 1 later, 0.2 plus 1.3, 1.5. Yeah, it looks good. And then that minus the 1.3 is over here. Now we just have to track that other seed value, which indeed was like 0.5 something, plus 1 period and minus 1 period. So we're almost done. Now let's remember what it was. Oh, is 0.481. Okay. 0.481, 0.481 plus 1.366. and 0.481 minus 1.366. Now, exactly how far you go forward or backward by periods is really going to depend on exactly what your interval is, and that's a totally realistic part of the problem. And so we can just go ahead and write that down. 1.568. You know, now I'm going to start going ahead and rounding. And then, oh gosh, I don't want to try and do that in my head on the video and just embarrass myself. So minus 1.164. And I'll round it. Okay. And then the other ones, 0.48. Just finishing off with the decimals. So 1.85, let's round it. And this one minus 0.8, let's say 89. Okay, so there's our 6 solutions. These ones rounded and these ones. And that's how that kind of problem is going to work.